Now, the notion of instantaneous frequency is really important for the idea of additive synthesis, because we would like to be able to control our sinusoidal oscillator such that it follows some sort of frequency trajectory. To better understand the idea of instantaneous frequency, let's begin with signal y of t, which is sine of theta of t, and theta of t would be the phase, and it's a time-varying phase, so we can say that theta of t is the phase function. Now, if we begin with a frequency trajectory f of t, how do we get the time-varying phase theta of t that we need? Well, it turns out that the frequency, when expressed as radian, or angular frequency, excuse me, in radians per second, we say omega t is actually the derivative of our phase function. So omega t then would be our frequency trajectory specified in radians per second. So we could say that our frequency trajectory in hertz, when we multiply that by 2 pi, we have the frequency that we need. Now, to solve for the desired phase function, I need to integrate both sides of my expression. 2 pi is just a constant that we can pull out of the integral. So our phase function then is essentially the integral from 0 to t of the instantaneous frequency. So you can, if you think about the area analogy for the integral, you say we're integrating, we're adding up the area underneath our frequency trajectory. Now the instantaneous amplitude, that's perhaps a little bit easier to grasp. That simply says that the signal y is our oscillator, that is sine of theta of t, times the time-varying amplitude a of t. So that becomes our expression for a single partial. And we see the frequency trajectory then shows up inside this integral. We solve for our theta of t, and here's our amplitude trajectory.